something does happen sometimes. Hello everyone, my name is Cao Tianjiao, and in the next few minutes, we're going to take a look at L'Hopital's rule or Bernoulli's rule. So, if you search L'Hopital's rule on Wikipedia, you're going to something like this. I know a lot of numbers and symbols, very intimidating. So we are not going to use that yet. Let's try something new. Let's try to solve Bernoulli's financial problem. So imagine yourself as a lender in Paris, and Bernoulli himself one day walked to the office to ask for a loan. Now your name is Shylock, so you decide to shut him up a little bit. You said, "Of course, Monsieur Bernoulli, here's $1 delivery comes for. Please use it freely this week and just pay it back next week. Of course, there will be some interest, and the interest shall be counted in this way." Then you look at the paper and, alright, he said, "I'll just have to pay you back as soon as possible." So Bernoulli took the money and walked out of the office happily. Only then did he realize a problem. Okay, now when Bernoulli said that he wants to pay you back as soon as possible, he means that he's going to pay you back at the very moment that the clock strikes 12 on the midnight of Monday, which means that this x here have to be some number that is extremely close to 0. So what would happen if this x is some number extremely close to 0? We will try. This x here would actually become something like n0, and this thing 10 to the power of x minus 1, 10 to the power of x became something extremely close to 0, and minus 1, it became 0. So that does make sense. This is nothing. We does not know what this means. However, this thing have to make some sense, or otherwise Bernoulli wouldn't be possible to pay his debt. So here's the problem. Bernoulli have to make something that is senseless into something that is understandable. To do that, Bernoulli defined two functions. First, Bernoulli thought, well, I'll just make u to f of x. And I'll just make u, this x here, to g of x. Bernoulli also defined a number x0. He made x0 a number that is extremely close to 0. So now here, that interest, Bernoulli wants to know how much is that interest. It becomes phi x0, phi of x0, and that is actually f of x0 over g of x0. So that still doesn't make sense, right? But there has to be some transformations. And how do you transform something like this? Well, as you can recall, you've learned in school that something like this, a over b, actually equals to a minus or plus 0 over b minus or plus 0. It also equals to a times c over b times c, or a over c over b over c, as long as c is not 0. So here, Bernoulli did something quite similar. He decided to subtract 0 from here. And where do you find that 0? Well, you can see this thing. F of 0 is 0 and g of 0 is 0. So he did something quite simple. He minus f of 0 here and minus f of g of 0 here. And that is quite smart, because Bernoulli looked at it and thought, well, this looks something like my friend Leibniz does. He created something called derivative. And to do that, I'll just have to divide it by x0 minus 0 here, and divide this thing by x0 minus 0 here. And now it actually becomes this very simple, very elegant thing, f pi of x, f pi of 0 over g pi of 0. Okay, a quick introduction to derivative. So let's say if you want to know the derivative of this point of this function hx here. You draw the graph of this function and you point this point and you draw the tangent of the point. So what you get now? You want to know the derivative of this point. All you need to do is to calculate the slope of this tangent here. So how do you get the slope? Well, you choose a point that is extremely close to this point. So let's make this point this. This delta x here is something that is extremely close to 0. So now, since these two points are so close, that line that you draw between them is actually the tangent line of this x1, this point here. So that slope you need is this. h of x1 plus delta x minus h of x divided by x1 plus delta x minus x1. So that is the derivative you want of this point. That is h pi of x1. Okay, now back to this point. Now we have transformed this phi of x0 into this f pi of 0 over g pi of 0, which you do some calculations, you will notice that this is the natural log of 10 over 1, which is the natural log of 10. Okay, so now here we are. We finally know that the interest Bernoulli shall pay you is this, the natural log of 10 livre. So all Bernoulli needs to do is that he have to walk into your office on that very moment and smash those 1,000 livre of debt and this natural log of 10 livre of interest onto your desk and walk freely away. He also discovered something that we now call it the Bidhouse rule, though, well, due to this small incident, we might be able to call it Bernoulli's rule after all. So, well, that is actually only the case 1 of the Bidhouse rule. Now it's time to get that Wikipedia page back. Okay, so what the Bidhouse rule states is that for a function, phi of x, which could be written in the form of f of x over g of x, when you pick an x that's extremely close to c and get something like 0 over 0 or infinity over infinity, you could calculate this thing in this way, f pi of c over g pi of c. As long as this g pi of c is not 0, it's okay. Okay, now you might wonder, why is there infinity? Well, there's actually a lot of things written on Wikipedia that you could read, which is too long and too complicated. I couldn't write it here. But let me provide you another way of thinking. Let's say we both know that this 1 over positive or negative infinity is something that is extremely close to 0. So by saying that, you could actually transform this infinity over infinity to something like this, 0 over 0. But one thing that you should notice is that although this thing could be extremely close to 0, it would never be 0. So that's going to create a problem, and to solve that problem you need something very creative, and I think you might want to try that, so good luck with that. So that's the Bidhouse rule. One thing we should notice is that in order to solve the problem, Bernoulli actually makes the equation more complex for a little while, then it transformed it into something very simple and elegant. We were often told that we shouldn't complicate things, but the truth is, complexity is often the road that we must take to reach our goal of elegance and simplicity. So I think that's something worth learning. To know more about the Bidhouse rule, please visit Wikipedia. You can find a lot of explanations and references on it. Thanks for watching. Goodbye.